information about what the graph looks like. Remember, that's really our question is, what does the graph look like? So what can you say about this first one? What do you already know about the graph? Did you want to say it? Yeah, it's a parabolic shape. And where are you looking to see that? Yeah, the exponent on the first term. Folks, the leading term really carries a lot of information about the graph. And this leading term there is x to the fourth. It's an even power, so it's some sort of parabola. It's a parabolic picture. So I'm just going to put a little picture here. Is there anything else we know about it? Oh, and by the way, is it facing up or facing down? It's facing up because it's positive. So is there anything else we can say about that polynomial right now? Yeah?
I have a question.
Yeah,
if you eliminate 3x4 with the minus 3, that goes out. So doesn't that it won't be a parabola, it will be the other way?
What do you mean if you eliminate this term?
Eliminate that term because you got a positive 3x to the 4, so minus 3.
Oh my gosh! That is a very terrible typo. I'm so sorry. Okay. That should have been a square.
Okay, fine.
Sorry, yeah, that would have been a real trick question.
I
Like,
say
aha, those terms cancel. Yeah, sorry, that was not supposed to be a trick question. That was just a typo. Okay, so yeah, we look at the leading term and it tells us if it's parabolic. So we know that if it's x to the even power, it's a parabola shape. Whereas if it's x to the odd power, then it's a half up and half down shape. So that's one thing we know. That's called end behavior. So end behavior is one big idea we talked about. What does the end of the graph look like? There we go. Yeah, as in where do the tails go? The tails either go both up to infinity, both down to infinity, or one up to positive infinity and one down to negative infinity. Those are the only choices for the tails, because they're always going to be going up or down to infinity. Okay, what can you say about this polynomial?
It's parabolic.
Is it also parabolic? Why?
Yeah, because you add up all the x's and the x to the 4.
Yeah, because you have, if you were to multiply this all out using FOIL and distribution, you would end up with something that looks like x to the fourth plus something x cubed plus something x squared plus something x plus something. If you were to actually multiply the whole thing out. So if you did multiply the whole thing out, it would be x to the fourth, and therefore this thing would also be a parabolic shape, at least as far as its end behavior goes. By the way, would it be positive facing up or negative facing down? Positive facing up, because all these x's are positive, so when you multiply the whole thing out, it would end up with a positive x to the fourth. Okay, what would this polynomial look like? What would be the degree of this polynomial? What would be the highest power on x? 3 this time. So it'd be x cubed plus something. We don't know what the rest of it would be unless we actually multiplied it out. And so this particular graph would look like this. That would be the end behavior. Now, there's a lot more we can say about this. What else can we say about this polynomial? We know where the what? To the what? The zeros, you mean the x-intercepts? Yes, we know the zeros, the x-intercepts, the roots. Those 3 words are all synonymous, right? So just by looking at the opposite sign of each of these numbers, we know the x-intercept. Another word for that is the root. Another word for that is the zeros of the function. So why are we allowed to look at each of those binomials and say, aha, that's the x-intercept? What rule or property allows us to infer that?
Because you equal it to 0 each.
Right, because ideally you're setting this whole thing equal to 0, and then I think I heard someone say the zero product rule. Did someone say that? Okay, how you did, Tanya? So the zero product rule says, well, if the whole thing equals 0, then this times this times this times this equals 0. So either this equals 0, or that equals 0, or that equals 0, or that equals 0. And when you set one of those equal to 0, like x minus 3 equals 0, as soon as you do algebra, it changes the sign of that number, and that tells you the number that if you plug it in, the whole function would equal 0, which is therefore the x-intercept. So yes, each one of these is the x-intercept, which allows us to do a lot more than just say that it's parabolic. We can actually now go in and make a fairly nice graph and say, well, the x-intercepts are at 3, at 1, at -2, and at -4. And I know my end behavior looks like this. And so now I know I can go like this. And now I have a pretty nice graph. I know a lot about what my polynomial looks like. Just by considering the end behavior, by knowing the highest power on x was 4, and by looking at all those x-intercepts, I mean, that's fairly sophisticated. Newton or Leibniz in the 1600s would have been impressed if you could make that sketch of the graph and say, well, generally speaking, it looks like that. They'd say, well, you have a TI-82. right? They'd be impressed. Okay, likewise here, each binomial factor is going to tell you an x-intercept. Okay, so those are the big ideas we looked at last time. Who can tell me the y-intercept? Well, let me go back up to here. What's the y-intercept of this function? Yeah, it's just 10. The last constant term is always the y-intercept. So this is important that you memorize this, that each binomial factor is an x-intercept, whereas the last number is the y-intercept. So what's the y-intercept of this?
Total everything else.
Well, total in what way?
Meaning taking the -3, -1, +2.
Yeah, straight up multiplying them, not changing the sign. We only change the sign to get the x-intercept. If you wanted the y-intercept of this function, you'd have to multiply all this together, distribute everything, and then the very last number is the product of just -3 times -1 times 2 times 4, which is 24. So in this case, then, the y-intercept of this function would be 24, which means I can go back to my graph now and put a little dot right there on the y-intercept, and now I know that's 24. Really, truly, folks, this is quite sophisticated. I have an x-intercept at 3, at 1, at -2, at -4, and my y-intercept is 24. That's a whole lot of information to know without even touching your graphing calculator. Right? That's very impressive. Okay, and likewise, what's the y-intercept of this function? 7 times 5 is 35, times 3 is 105. So the y-intercept for that function would be 105. Okay, moving on. When you do synthetic division, what does the last number represent? So let's just say that I have a polynomial and something like 2x to the 4th minus 3x cubed plus 8x squared minus 7x plus 13. And so I take all those coefficients, 2, -3, 8, -7, 13. And then I do synthetic division with some number. I'll just do something simple like 1. What are we about to do? And again, I'm calling this a function, f of x equals all that. And if I plug a 1 in, and I do the process, I drop the 2, and then you multiply, add, multiply, add, multiply, add, multiply, add. What did we just do? We did what? I found the output, exactly right. I plugged 1 into that. That was, that's my number that I plugged into synthetic division. So I'm plugging a 1 in, and it equaled 13. So the last number represents the output if this is the input. So here's my input into synthetic division. Here's my output from synthetic division, which really means here's my input into the function, and here's my output from the function, which, what's that?
Wouldn't that be the y-intercept?
Wouldn't that be what?
The y-intercept.
Well, that's interesting. It also happens to be the y-intercept as well. So it looks like this particular function, we know the y-intercept is at 13, and then at 1 unit later, my point is also there. So presumably, maybe it did a little wiggle or something. Yeah, we know both of those things. We know the y-intercept is 13 from that number, and we also know that the coordinate is 113. So there must just be some sort of wiggle there. We don't know what the wiggle looks like. That could have been a maximum of the function, or that could have been a minimum of the function. We're not sure. We would have to do more research. But what else do we know? Now that f of 1 equals 13, we also know, I already kind of put it there, that if you made a table of values, your input would be 1 and your output would be 13, and therefore what do you have on the graph? The coordinate 113. So we know the coordinate 113 is on the graph. Those are all different ways of saying the same thing. If you input 1 and output 13, that means f of 1 equals 13. That means on the table of values you have 113, and that means the coordinate 113 is on the graph. It's important to be able to look at it from all those perspectives, because synthetic division is giving us a lot. And I think that answers our questions. When you do synthetic division, what does the last number represent? It's the output of a function. What do the first and last number together represent? Coordinate. All right, so that's what we did last time on Wednesday. So before I move on, does everyone in here have the packet for section 3.1? Well, for chapter 3? Everyone has it? I think everyone has it. I only have one extra copy if anybody needs one. All right, then let's see. Today is what, September 24th? Is it really? Yeah, it is. So today's September 24th. The syllabus said we'd be on 3.3. We're actually starting with 3.2 today. So we'll do 3.2. We'll probably finish that and get into 3.3. And then on Wednesday, that's our time to wrap up the whole chapter. So theoretically, we're going to finish chapter 3 this week. And then next week we'll do chapter 4. And then the next week we have a review day, which is also a catch-up day. And then you have a test coming up on October 10th on chapters 3 and 4. Before we actually start chapter 3.2, I'd like to review some homework questions from the online More website. I only got a couple emails from you over the weekend. Just a few of you emailed me, and I'm glad that you did. Let's talk about that. When you're on your website and you're doing your problems, I would really like to encourage all of you to use the post this question to forum link. A few of you have, and I think that's great because then you ask your question and I answer you, and now everyone in the whole class just benefited from getting to see how to solve that problem. If you still want to message me personally, maybe you're shy, maybe you're embarrassed, maybe you don't want to post it to the whole class, I get it. But if you're willing, please post it to the whole forum so that everybody gets to benefit from your question. Because the questions I receive are very good questions. So that's one thing I'd like to say. I chose a few problems that I want to go over with you from the homework. So definitely follow along. If you've already finished the homework, then you can just listen along anyway. But if you haven't finished the homework, I'm about to give you some really good helpful tips. This is the homework due tonight at midnight. So, question number 3. Number 3 says, find the degree, leading coefficient, and maximum number of zeros. So the degree is what? By definition, the degree is the highest exponent on x. So that's just 5. Now, what's the leading coefficient? Yeah, just 3. If it had said the leading term is 3x to the 5th, and that tells me the end behavior. The leading coefficient is just a number on that term, which is just the number 3, which really just tells you that it's positive, which means if it's a parabola, it's facing up, or it means if it's a cubic, it's facing that way. Okay, now, here's this one, maximum number of real zeros. I realized after class ended that we didn't go over this. The maximum number of real zeros tells you this, and this is amazing, that in a polynomial, the degree, like x to the 5th, that's the maximum number of x-intercepts. That's the most number of x-intercepts you can possibly have. And remember, that's what zeros means. Zeros is just a word that means x-intercept. So, as a general rule, whatever your highest power of x is, that's the maximum number of x-intercepts that you can have. Now you might say, well, is it the maximum number or is it the number? So I want to give an example. Let's say that I had a function that was x to the 5th. So f of x equals x to the 5th. And then, more terms, which I won't write down. In that particular case, what that tells me is the most number of x-intercepts I'm going to find is 5. And I think that's obvious. If you had an x to the 5th, and then you actually factored it out, how many factors would you get? 5 factors, because they would then be able to multiply back together to equal x to the 5th. So if you can factor x to the 5th into 5 factors, then that means you have 5 x-intercepts. At most, 5 x-intercepts. Let's say the function looked like this. So here's my function. Since it's x to the 5th, my end behavior goes like this. And my function goes wiggle, 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 wiggle. Okay, so there's my x to the 5th. I have 5 x-intercepts. However, now, what would happen if I took my whole function here and I added, let's just say that I add 20 to it. Remember, adding a number at the end shifts the whole function up. So now what would happen if I shifted that whole function up? My function would go up, and my wiggles would be up here. Now how many x-intercepts do I have? Just the 1. Because I effectively shifted all the wiggles out of the way of the x-axis. So it's the same function, I just shifted it upward, but those wiggles now miss the x-axis completely, and you only end up with the 1 x-intercept. So, again, what that tells us is that the degree, the maximum, the highest power at x, is the most number of x-intercepts. You could have less than 5. You could only have 1. Or in the case of a parabola, for instance, here we go. What if you had f of x equals x to the 8th? So first of all, how many x-intercepts could I have? I could have 8. And in that case, maybe the graph looks like this, where I have x-intercept 1, 2, 3, 4, 5, 6, 7, 8. And then since it's even, my end behavior would look like this. And then it goes wiggle, 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 wiggle. But then what if I took that whole function and added, say, 30 to it? The whole thing would shift upward. And that would pull all the wiggles out of the way of the x-axis. And now how many x-intercepts do I have? None. right? So again, 8, the degree, is the most number of x-intercepts you could have. You could have fewer. You could have none. So that's how you would respond to that question. The maximum number of real zeros in this case is 5. So let's just check, see how we did. Oh, good, we got it right. Questions about that? Okay, up. Number 8. Number 8, I think, is fairly similar. It says, what is the least possible degree of the polynomial graphed above? The least possible degree. So let's just consider, first of all, how many x-intercepts do you see? There are 2 x-intercepts. So I want you to imagine it. What would our function look like if there are 2 x-intercepts? How many binomials do we have? At least 2, right? We have to have at least 2 of these in order to have 2 x-intercepts. And if each of those has an x in it, and then I multiply it all out, I would get a function that's x squared. But so it has to be at least 2. But could it be more than that? Could I actually have a whole bunch of binomials? I could, especially if it's the same thing twice. So for instance, look, this x-intercept is negative 1, 2, 3, 4.5. I'm just going to call it 4. And this is at 1, 2, 3, 4, 5.5. I'm just going to call it 5. I could have x minus 4, x minus, I'm sorry, that'd be x plus 4, and x minus 5. So I've got some duplication built in here. This x-intercept is listed twice. It's still just one x-intercept at negative 4, and this is still just one x-intercept at positive 5. But when I multiply that out, I could get x to the 4th. So you see, when you look at a graph, the question is, what is the least possible degree of the polynomial? The least possible degree is 2. It could be higher, but the smallest is 2. So that's 2 different ways to think about it, and you have to think carefully because that could be confusing. The least possible degree is the number of x-intercepts you see on the graph. It could be more. Whereas the most number of x-intercepts is the degree on the polynomial. It could be less. Right? That's very tricky to think about. Okay, so that's number 8. What's the least possible degree? Gosh, what do we do? Just type in the number 2? Yeah. Okay, so that was number 8. Questions about that, folks? I hope that you're finding this helpful. I just imagine that these were some of the trickier problems that everyone would benefit from seeing. Okay, so then the next one I wrote down was 4. I think this is about end behavior, and they're giving it to us in a way that we didn't talk about. It says, describe the end behavior of f of x equals negative x to the 8th. So take a look at this, negative x to the 8th. So what's the end behavior there? Because it's an even power, we're looking at a parabola, but because it's negative, it's facing down. And so we have something that looks like this. Now, how do we answer the question? It says, as x approaches negative infinity. So that means as you move this way on the x-axis, as x approaches negative infinity, what's our y doing? Our y is going to negative infinity as well. And so the answer here is, as x goes to negative infinity, f of x goes to negative infinity. So look at that notation. It's saying, as x goes to negative infinity, meaning it's going to the left, what's our function doing? F of x goes to negative infinity on the y-axis as well. So we're talking about x-axis, then we're talking about y-axis. Let's try the next one. It says, as x goes to positive infinity, so as I move to the right, what's my function doing? Also going down to negative infinity. So then we'd say f of x goes down to negative infinity, and we click submit, and they're both right. So that's what that notation means. Just in case you got to that and you're like, whoa, what does that mean? Of course, you might have just clicked the video and watched the video. Maybe you already answered that question. Okay, well, let's see. That was 4. I think number 5 is very similar. Yeah, 5 is similar. Okay, so that leaves us 10. Let's look at 10. Given this polynomial, okay, I had quite a few people email me about a problem like this. So given this function, what's the p of n intercept? And then what's the n intercept? Well, let's just talk about that notation. Because we're used to seeing things like x and y. So how do we even know what that means? What's the P of n intercept? Because we know that normally this is x and y, which means normally this is x and f of x. But in this particular problem, our variable is n, and our function is P of n. So when they say, what's the P of n intercept, what are they really asking for? The y-intercept. That's what they really mean. The P of n intercept is really just a y-intercept. So that might take a second to feel comfortable with, because they're using different variables and different letters. Okay, so what is the P of n intercept? How do we find the P of n intercept? You look at the constant term. This polynomial didn't have a constant term, and so you could infer that it's 0. Or remember, well, how do you ever find a y-intercept? What do? You just plug in 0. And if I plug 0 into this function, 0, 0, 0, the y-intercept is 0. So now for sure I know that the P of n intercept is 0. Notice, however, it says give the p-intercept as an ordered pair. So if my y-intercept is here, what's that coordinate? 0, 0. And that's what they mean by ordered pair. Ordered pair really just means coordinate. All right. So yeah, lots of new vocabulary. You might not have seen some of this vocabulary before. Oh, I'm very sorry. I just wrote that on the wrong line, didn't I? That's confusing. Here we go. The y-intercept was 0, 0. There we go. Okay, so now what's the n-intercept? This is where the real work begins. In order to find the x-intercept, how do you solve for an x-intercept in general? You set f of x equal to 0. Right? That's always our method. If it's a parabola, you can do the quadratic formula. If it's a polynomial, maybe you can factor it. But no matter what, you take your function and set it equal to 0. So here's our function. P of n equals 2n to the 4th minus 10n cubed minus 12n squared. I'd like to find the x-intercepts. What's one way we can find the x-intercepts? Probably the easiest way. Graph it. Quite a few of you, that was the method you used, and that's fine. You can just graph it. Although we probably want to keep in mind that graphing it on the Desmos, while that is simple, and by the way, you have to use the variable x. You can't use the variable n. So 2n to the 4th minus 10x cubed minus 12x squared. There we go. So just keeping in mind that you have to use the variable x, not n, when you type it into Desmos. There's our x-intercepts, and we're done. So the x-intercepts were -1, 0, and 6. So going back to my original thing here, I think you have to type the x-intercepts in order. So you'd have to type in -1, 0, and 6. And so those would be the x-intercepts. And you solve the whole thing by just graphing it. However, let's say that you don't graph it to find the answer because it's on the test and you can't use Desmos during the test. You could use a graphing calculator, right? Your graphing calculator would tell you the x-intercepts. Or you would just actually have to solve this problem. So how do we solve this equation? What's the first thing you do? We do want to isolate the variable. Yeah, we have to solve for n. We can factor out quite a bit. We can factor out a 2, and we can factor out an n squared. So we take out 2n squared, leaving behind n squared minus 5n minus 6. So that was our first part. We factored out 2n squared. Then what do? Then we just factor this. This is a simple polynomial. You can factor it. You can say, what do you multiply to get 6 that you add to get 5? This one's tricky because it could be, to get 6, -6. It's either 1 times 6 or it's 2 times 3. So what's the appropriate answer? This one's tricky. We need to multiply two numbers to make a -6. That means we have to have a positive and a negative. And they have to add to make -5. Yeah, it's got to be this one, the -6 and +1. You might accidentally say 2 and 3, because -2 plus -3 equals -5. But -2 times -3 would be a +6, and that's not the correct sign. So it'd have to be 1 and a -6. So now we have 2n squared times n plus 1 times n minus 6. And now we can use the zero product rule and say, well, if these three things multiply to equal 0, then either 2n squared equals 0, which means n equals 0, or n plus 1 equals 0, which means n equals -1, or n minus 6 equals 0, which means n equals 6. And are those the same x-intercepts that we found from the graph? They are. -1, 0, or 6. And again, just keep in mind that I think you need to type those in order. I think I had a student who emailed me and the program didn't take it, and then I tried it myself, and it only worked when I typed them in order from smallest to greatest. All right. Questions? Okay. Well, then I think the last, wait, 10, 12. 12 might be similar. This one had a cube root involved, and I think that's worth mentioning. Here, the same thing. You have a function. You want to find the r-intercepts and the f of r-intercept. Well, first of all, the f of r-intercept is always the easiest because that's just the y-intercept. So if I wanted the y-intercept here, what's the y-intercept? Just 10. Right? Because if you plug in 0, you just get 10. So what's the r-intercept? Well, everyone, remember, if you want an x-intercept, you take your function and you set it equal to 0, because that's always going to give you the x-intercept. So that gives us negative r cubed equals -10, and I divide off a negative. That gives me r cubed equals 10. And if I cube root both sides, be very careful there, cube root both sides, then r is equal to the cube root of 10. That's apparently the x-intercept. So how do you type that into the program? I had at least a couple people ask me, how do you type in a cube root? Well, first, let's clarify, how do you do a square root? Yeah, SQRT, that would be the square root of 10. But that's not the right answer. We want the cube root of 10. Well, to my knowledge, you just can't write cubert. No, that doesn't work. It's only for the SQRT. So to do a cube root, well, first of all, we might just check this little yellow arrow here, because the little yellow arrow often gives you helpful tidbits. And let's just look here. We can type in whatever we want here, and this is, hey, there we go, the cube root of 10. So there's a button right there that actually does cube root of 10. And gosh, it just knew from context that I wanted a cube root as opposed to anything else, so that was nice of it. But the other thing you can do is if you want a cube root, it's 10 to the power of 1/3. Oops. 10 to the power of 1/3. Oh, why is that not working? 1/3. There we go. If you want a cube root, it's to the power of 1/3. This is a review of exponent notation from another class. I'm going to write it over here. The square root of x is the same as x to the 1/2. And the cube root of x is the same as x to the 1/3. And the fourth root of x is the same as x to the 1/4. You just have to be careful that when you do an exponent to a fraction, you have to type in your calculator x caret parenthesis 1/3. If you just type in x caret 1 divided by 3, you could get a calculator error. It could do something not what you expected. Your calculator will think this means x to the power of 1 divided by 3, which is really x to the power of 1 divided by 3, which is 1/3 x. That's very different than a cube root of x. So when you do x to the power of 1/3, make sure you put the 1/3 in parentheses. Okay. Well, let's see. I think I had one other problem that I wanted to look at. 16. Yeah, 16. There we go. Okay. This is a great question to lead into what we're doing today. This will be our last review question. I hope that this has been helpful to review this together. Given the function phi of x equals x minus 1 squared times x minus 9, find the y-intercept, the x-intercepts, and the end behavior. So this is asking for the whole thing. This problem is essentially leading you through what you would do mentally anytime you saw a polynomial. So first of all, what's the y-intercept? Well, we don't know yet. I would probably take that polynomial and write it out. So it's x minus 1 times x minus 1 times x minus 9. Because remember, to find the y-intercept, you multiply the actual numbers. So what's the y-intercept? -1 times -1 times -9? -9. So there's my y-intercept. And then what about the x-intercepts? Well, for the x-intercepts, you take the opposite value of each number in there. So my x-intercepts are simply 1 and 9. Right? So now I know my x-intercept is, the smallest one is 1, and the largest one is 9. They're always going to ask for smaller than larger. And then they're asking for end behavior. Well, this is 1, 2, 3 x's. This is really an x cubed. So my end behavior, if I have an x-intercept at 1 and at 2, 3, 4, 5, 6, 7, 8, 9, my end behavior is a cubic. So I've got one tail going down, one tail going up. And now the question remains, how do I trace in the rest of the wiggles? Remember about multiplicity. So this is really x minus 1 squared times x minus 9 to the first. What do we remember about multiplicities? What do you know if the binomial is to an even power? What happens at that x-intercept? It's a bounce. So that right there is a bounce. Whereas what happens if the power on the binomial is an odd power? It's a slice. So now I go to my graph, and I will actually write bounce, and I'll write slice just to remind myself, because now when I finish off my graph, it's going to go bounce and slice. And so that's what our actual polynomial looks like. And now I can answer my last question about end behavior. As x goes to the right, my function goes up to infinity. So that's up to infinity. And as x goes to the left, my y function goes down to negative infinity, and that would be negative. Okay, so that's the whole problem. Do any of you think we got those answers right? Let's find out. The y-intercept is negative 9. The x-intercepts were, what was it, 1 and 9. And then this went to, oh, I just have to write positive. And here I just have to write negative. And let's see. Oh, goody gumdrops, that was it. Okay, well, folks, that was already a goodly amount of information. I feel like we should take a break. But we won't, and we'll just keep going. So, here we are. I do have a joke for you to get us started. You're like, started? We've already been doing class for 35 minutes. But now we're about to start. And so, did I already tell you my joke about past, present, and future? Yeah. I did. Whoa, that sounded like a groan. Yeah, you told us that joke. Oh, no, that was a good joke. Okay, well, here's another good one. Where do hardcore kids go camping? Where do hardcore kids go camping? Everyone, you're going to love this one. You'll want to watch. Where do hardcore kids go camping? In tents!
Oh my God.
Yeah, in tents! All right, see, I knew you all would love that joke. All right. So everybody go ahead and open up your packet, your chapter 3 packet, 3.2. 3.2. We will continue on from there. Now I would say that section 3.1 was all about recognizing visual attributes of polynomials on a graph, provided you already know how to factor it. Section 3.2, 3.3, and 3.4 are going to be how do you factor. So I just want to show you our goal. Oh, that's a lot of. What's our goal? For the whole rest of chapter 3, our goal is to transform this f of x equals x to the 5th plus 3x to the 4th minus 7x cubed plus 8x squared minus 10x plus 37. So our goal is to be able to take a polynomial written in general form and to transform this into this. F of x equals factor, 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 factor. All right, so this is our goal. Our goal is take a polynomial that's just written out as a bunch of terms and then factor it into products. Why is that our goal? Why is this our goal? What do we gain out of factoring the polynomial? What do we gain? What information do we gain? Yeah, the zeros, the x-intercepts. By having it in this form, we have the x-intercepts. What information do we have in this form? If we just have this form, what information do we have? We have the end behavior, and we have the what? the y-intercept. So notice that if you just have a polynomial in standard form, all you know is the end behavior and the y-intercept, and that's not much. Whereas by factoring it, you just gained all the x-intercepts. And then you have everything you need. You need all three of these. You need end behavior, y-intercept, and x-intercept, and then you can say, you know what the graph looks like. So this is our goal for the rest of this week, is how do I take a polynomial and how do I factor it? Other than typing it into a computer and asking it to do it for you. So we already started doing this the other day in class. Let's go ahead and try this. The first couple problems, they actually want us to do long division. Now I'm going to tell you right now, I'm not going to test you on long division. It's not going to be on the test. It's not going to be on the final exam. Because long division is just kind of this antiquated thing that we do. But nevertheless, I'm going to show you how to do it. And so everyone, I want you to write this down. I want you to experience it. Just know that we're not going to do it on the test. So I want to divide 4x squared plus 3x minus 1 by x minus 3. And so you set it up like a standard division problem. 4x squared plus 3x minus 1 divided by x minus 3. This is not synthetic division. This is normal division. So go all the way back to your grade school days when you had to divide 5 into 241. Right? How do you do normal division? First of all, when's the last time you did normal division on a piece of paper with a pencil or a crayon? Anyone know the last time you actually did division? Was it years ago, or was it months ago, or was it yesterday? Was it this morning? I mean, maybe it's been a while. So let's just remember, how do I do division? Does 5 go into 2? No. Does 5 go into 24? Yes, you put 4. 4 times 5 is 20, and then you subtract, and you get 4. Then what do? You drop down the next one, and you get a 1 there. Now, does 5 go into 41? Yeah, 8 times. So you go 8 times 5 is 40, and then again you subtract, and you get 1. Now, do I have to keep bringing more down? I could put a decimal spot and then put a 0 and then drop to 0, or I could just be done. The answer is 48 and 1/5. Right? So I could go ahead and say that 241 divided by 5 is equal to 48 and 1/5. Okay, so does that look familiar? That reminds you of being in elementary school, doing division. So we'd like to do something similar with this. Now, just looking at this example and saying, yeah, sure, we did that. And now saying, okay, now do it again. You might look at this and say, what? Like, how would you even begin to do division? But it's not that bad as it turns out. So let's try it, folks. Look at your x minus 3. We're always just going to look at the first term there. X minus 3 goes into 4x squared plus 3x minus 1. What do you have to multiply by x to get 4x squared? 4x. Right? So do you all agree on just that part? That what would I have to multiply by x to get 4x squared? I'd have to multiply 4x. Because x times 4x is 4x squared. This is how the process works. So now that I have that number on top, what do? Just like before, I did 4 times 5 is 20. So I'm going to do 4x times x minus 3 and write down the result. So 4x times x minus 3 would be 4x squared minus 12x. Right? So we started by saying, what would I have to multiply times x to get 4x squared? The answer is 4x. And then you do 4x times x minus 3. If you need to see that visually, here's a reminder. 4x times x minus 3 is a distribution problem where you have to multiply 4x times x to get 4x squared, and then 4x times negative 3 to get negative 12x. And I write down that result. This is kind of all in your head. Okay, so now what do? What do we do in normal division? Subtract. So we subtract, and subtracting really means you change the sign on both of these. So this is positive 4x squared, I'm going to make it negative. That's a negative 12x, I'll make it positive. And now I'm actually going to add these together. It's just easier to do it that way. I'm going to add these together. So 4x squared minus 4x squared is nothing, and 3x plus 12x is 15x. So we did subtract. But we subtracted by changing the sign and then adding. Okay, so now what do? Oh, yeah, drop the negative 1. Thank you very much. So we have to drop the negative 1. and now we do the same thing, but again. So we say, what do you have to multiply times x to get 15x? 15. So we write down now 15. So again, you multiply 15 times x minus 3. And again, if you have to see it visually, 15 times x minus 3 is a distribution problem. And so that would be 15x minus 45. And so it's 15x minus 45. And we're going to subtract, which means you change the signs and then add. So those cancel out, and you end up with 44. So this is called long division. Now we're done, because we don't have anything else to drop down. So at this point, just like before, I drew my little arrows to say 48 and 1/5. So again, this is 4x plus 15 and 44 x minus thirds. The answer is 4x plus 15 plus 44 x minus thirds. So you can tell that in both cases, you end up with a whole number and then a fraction. This was 48 and 1/5. Now this is 4x plus 15 plus 44 x minus thirds. Now that we've done it, wasn't that fun? You're like, wow, that's great. Super. Have you ever done that before? Maybe you have, maybe you haven't. Maybe you did it in high school, I don't know. So we did write it down as they said. So now notice, write the polynomial in the form p of x equals that times that plus the remainder. They want us to write it down differently. The way that would be written down in the other way, they're saying to take the polynomial, the original polynomial, 4x squared plus 3x minus 1. They're saying that that is equal to the divisor. So that's the first part, t of x, the divisor. Where can I write all this? Here we go. This is the divisor. This is the quotient. This is the remainder. I would write all that down, folks. And so they're asking us to take the original polynomial and rewrite it as the divisor times the quotient plus the remainder, which is the divisor, the quotient, and the remainder. And therefore, we're saying that this polynomial, 4x squared plus 3x minus 1, is equal to, all right, what did we have? The divisor was x minus 3. The quotient was 4x plus 15. 4x plus 15. And the remainder was 44. Okay, so that'd be the whole problem. Yes? Well, they're both a normal way of doing it. You can either write it down that way or you can write it down this way. They're both ways of doing it. They're just written differently because honestly, this is the answer to a division problem, whereas this is just factoring the original polynomial. So they are different. They're sharing different pieces of information. You might say, well, what did we gain out of doing this? You know, who cares? We took 4x squared plus 3x minus 1, and now it's factored into this plus 44. Well, what does that really mean? It means if I took this now and actually FOILed it out, I would get 4x squared minus 45 minus 12x plus 15x plus 44, and that would be 4x squared plus 3x minus 1. And is that the original? It is the original. So really the whole point of the problem was to take a polynomial and rewrite it in a different way such that you do have two things being multiplied together and then a remainder. Okay, I think that's all there is to say about it, and everyone can cross out number 2. Because this is not the method we're going to be using. We want to use synthetic division. Synthetic division is far more powerful and honestly simple. So I'm going to leave that up there because you're still looking at it. And let's do a problem using synthetic division. Actually, should we do the exact same problem with synthetic division? Would that be helpful to see the exact same problem by using synthetic? Yes. I think that would be good. So over here to the right where you crossed all that out, let's just use that space to do the same problem with synthetic division. So over there on the right-hand side, right below the number 2, let's do the same problem using synthetic division. So what's our original question? So this will be our number 2. It says take 4x squared plus 3x minus 1 and divide it by x minus 3. So this would be a good review. We'd like to divide those two numbers. And remember what we said last time. This was the thought procedure to help you work through this. We're saying, hey, I wonder if the numerator can be factored into something that has an x minus 3. Right? Remember, that was just a thought experiment. We said, hey, I wonder if this thing can be factored. And if it can be factored, I wonder if one of the factors is x minus 3. And why do we care if it's x minus 3? Because then it would cancel, and that would be convenient. So we said to ourselves, okay, here's a polynomial. I wonder if it can be factored. I wonder if one of the factors is x minus 3. And if that's the case, that one of the factors was x minus 3, what's the x-intercept? 3. And if the x-intercept was 3, that means the coordinate 3, 0 is on the graph. And that's your input-output. And that means that if I did synthetic division on 4, 3, negative 1, so I'm doing synthetic division on my polynomial, and I plug in 3, what should I get out? I should get out 0. Right? This is all a thought experiment. We're saying, if I was able to divide this polynomial, or I'm sorry, if I were able to factor this polynomial, and if one of the factors were x minus 3, that would cancel out and it'd be very nice. And so we're taking this to the logical end. We're saying, well, if it did factor into an x minus 3, then that would be an x-intercept, which means 3, 0 is a coordinate, which means input, output, 3, 0, which means if I did synthetic division, if I plug in 3, I should get 0. So now let's do the experiment. Let's actually do synthetic division with a 3. I drop the 4, and then multiply, add. Multiply, add. And was it a 0? No. So that means that our original thought experiment did not prove fruitful. There was no x-intercept at 3. And one of the factors is not x minus 3. So in other words, no. 4x squared plus 3x minus 1 cannot be factored into two factors, one of which being x minus 3. But we did just get some information. What information did we get? We got the coordinate 344. So now I do know that somewhere way up here, I do have a coordinate, which is 344. So I did get something. And there's a lot more that we got as well. So we might consider writing out the formula again here. What we just found out Right. I'm just thinking about how to write this down for everybody. The first thing we found out is that the remainder is 44. Well, that's true. Gosh, there's two different ways to write this down. I just want to make sure I tell it to you in the right order. We could go ahead and say the formula that they gave us. So let's write that down together as a group. P of x, I'm going to come over here. P of x is equal to d of x times q of x plus r of x. We'll want to memorize this formula, folks. So what are we saying? The original polynomial is the numerator that we were looking at, the 4x squared plus 3x minus 1. So we're saying 4x squared plus 3x minus 1 is equal to what? Well, I know for sure it's not equal to just binomial times binomial where one of them is x minus 3. However, it's equal to something very close to it. The divisor, first of all, this is our d of x, which is not just the number 3, rather this is the divisor, d of x. So I know that this, my divisor, is going to be x minus 3. I know that my quotient, so hold on, that's the divisor. This down here is my quotient, which in actuality, if you look at these last coefficients here, since I started with x squared, I go down to just x. So that's 4x plus 15. That's my quotient. So now I have 4x plus 15. And then this last part is my remainder. That's my r of x. This is my q of x, which is 44. I would say in order to do this whole process successfully, you really need to have this written down somewhere that you can look at, and you need to have all of these parts and pieces labeled so you know where you're looking. The last row of coefficients is your quotient, the very last number is the remainder, and the starting binomial was your divisor. So first of all, folks, did we get the same result? X minus 3, 4x plus 15, and 44? We got the same result, but using synthetic division. Is it easier? Well, I would say so, because look, this was the only work we did. We just did a little box of numbers where you multiplied and add, and you got the same coefficients without having to do all that long division business. Now going back to, who asked it? Somebody asked, are those the same? Was it you, Jose? Yeah, so are they the same? Well, here's what we really know. The original problem was 4x squared plus 3x minus 1 all over x minus 3. That was the original problem. And what we found out so far is how to rewrite 4x squared plus 3x minus 1. We know that we can rewrite 4x squared plus 3x minus 1 as this. So if you did actually do that, rewrite the numerator as x minus 3 times 4x plus 15, and then plus 44, and then divide all that by x minus 3, then you can take that fraction and split it into one part of the numerator and the other part of the numerator being combined through addition. And that would give you x minus 3, 4x plus 15 over x minus 3, plus 44 over x minus 3. And then what could you do with the first one? You can cross out those x minus 3's, and you get 4x plus 15 plus 44 x minus 3's, which was the original answer we got from the long division. Okay, right now I'm fearful that I just threw way too much at you. I just did way too much all at once. I need to break this down into simpler steps. So that's it for number 1 and 2. I wanted to show you how long division worked and the relationship between long division and synthetic division. But really, from now on, we're just going to do synthetic division. So let's go ahead and do a couple more synthetic division problems. Hey, by the way, did Kevin Palacios come in? Kevin, are you here? No? Okay, Corey, you're here. I want to give you the packets from last time. Okay, here you go, Corey. All right, so everybody, let's go on down to number 3. Now, folks, you'll notice on your packet, there's not a lot of room there. I would say there's not a lot of room. If you wrote really, really small, you might be able to do that right there. But I think maybe taking out a sheet of lined paper might be a better bet for you. So maybe take out a sheet of lined paper, or if you can, write really, really small. So here we go. Folks, first of all, circle this definition, because that definition is the core part of our process. And let's go ahead and do synthetic division a couple times. So first, we're doing synthetic division on the polynomial 3, -2, and 1. And we're dividing it by x minus 1. Now let's just keep in mind what we mean by that. If we're dividing by x minus 1, what number are we using for synthetic division? Regular 1. We're using regular 1. Even though that says x minus 1, we're changing the sign and we're using positive 1. This is something that is very often mistaken. People accidentally use the same sign and do -1, and then it doesn't work. But remember, we're trying to say, can 3x squared minus 3x plus 1 be factored into a term that has x minus 1? Remember, that's the thought experiment. And if there was a factor of x minus 1, that means we're really looking at an x-intercept of 1, which means we're thinking about the coordinate 1, 0, which means we're saying input, output. We're asking, if I plug in 1, will I get 0? So that's why we're putting in 1, not -1. So if you just want to have a friendly reminder to yourself, you put a little word to yourself right here that says change sign. But
Can I ask you one simple question?
What?
Is it because you're always changing the sign to the opposite sign? So basically, it's like saying x minus 1 equals 0, and you're probably
yes, absolutely. Because you're saying x minus 1 is equal. Yeah, that's
okay.
it. Yeah. Okay, so let's try it out, folks. We drop the 3. Now this is the easy part. You just do synthetic division. So you drop the 3, multiply, add, multiply, add. So first of all, is there an x-intercept at 1? No. There is no x-intercept at 1. That whole thought experiment was a failure. The coordinate 1, 0 is not on the graph. And in fact, the only coordinate we know of now for sure is the coordinate 1, 2. So we can say for sure that 1 is not an x-intercept. But now what I'd like us to do is just practice. How do we rewrite 3x squared minus 2x plus 1? Well, let's circle everything and define it. This was a representation of the divisor, which was d of x. This is a representation of the remainder, which is r of x. And this is the representation, well, once you put the variables back in, it started as x squared, so now it's just x. This is the representation of the quotient, which is qx. That'll be the first thing. Should make an anatomical diagram of what you just did. Label it all. Now we can go ahead and use the formula that they have there, and that is that synthetic division allows you to rewrite a polynomial p of x as a divisor times a quotient plus a remainder, which in this case is 3x squared minus 2x plus 1 equals the divisor, which is x minus 1. Keep in mind, when you want the divisor, you can always just go back and look at the original divisor. We were divided by x minus 1. So if you look here, now you have to remember to go back to x minus 1. That was your divisor. And then the quotient is 3x plus 1. And then the remainder is 2. That is always what you're doing every time you do synthetic division. When you do synthetic division, you're really just rewriting a polynomial as a factored polynomial with a possible remainder. Sometimes that remainder is a 0, and that's nice because then the 0 goes away, and you're just left with a factored polynomial. But when there is a remainder, then you've got that little number floating outside there. Okay, that's the fundamental process. Let's do it again, and then we'll take a break. So here now, we're saying 4x squared. We're going to do this and then a break. So now we're going to do synthetic division with 4, -5, 3. And so again, you're dividing by x plus 3. So what number are you plugging in? -3. We're saying if I plug in -3, will I get a 0? So let's find out. I drop the 4. That's multiply, add, multiply, add. Did I get those numbers right? Did anyone else get 54? Okay. Okay, again, I'm going to diagram all this, but I'm just going to use the symbols. This was my d of x. This is my remainder. And this, I started as x squared, so now this is just x, is my quotient. Now, you might start to visually see this, and you won't necessarily have to keep looking back at the formula, that each of these parts can drop down directly in order for you to write it all down. So I start with the x plus 3 times the 4x minus 17 plus the 54. I don't know if my blue arrows are helpful, showing how you take that information from synthetic division and dropping it into your rewritten polynomial. And keep in mind, what is all of that? That's another way of writing 4x squared minus 5x plus 3. That's what we just did. We just pseudo-factored 4x squared minus 5x plus 3 into the product of two binomials and a remainder. Everybody, we can cross out number 5. But I'm going to do another problem with you real quick before the break. I have to admit, if I could get away with not giving you any breaks, I would. But I'm going to give you a break, but let's just finish this next problem. Let's say we took a polynomial that we know is going to factor, like x squared minus 3x minus 12. I know that's going to factor. Because what multiplies to make 12? Wait, did I just write down the wrong thing? I just wrote down the wrong thing. Silly me. I meant 28. I know this is going to factor, because what multiplies to make 28? 7 times 4, and I can get a difference of 3 out of that. So I already know ahead of time that this is going to factor into x minus 7, x plus 4. Am I right on that? Did I do that factorization correctly? Yeah. Okay. But let's pretend we didn't know that. Let's just say, hey, I've got this thing, and somebody said, divide x squared minus 3x minus 28 divided by x plus 4. Right, so let's just see what synthetic division gives us from this procedure. Because I want us to see that synthetic division gives us a new way of factoring that you've never done before. So let's do the process. That coefficient is 1, so that's 1, -3, -28. And what number am I plugging in?
-4.
-4. So we do synthetic division, drop the 1, so that's 1, multiply, add, multiply, add. Now let's diagram this. I know that this is my divisor, this is my quotient, and this is my remainder. And I started with x squared, so now that's x. And now watch what happens when I rewrite all of this. Woo. I get that my original polynomial, x squared minus 3x minus 28, is equal to x plus 4 times x minus 7 plus 0. And that's really cool. That's really cool because the plus 0 goes away, and now we just see that x squared minus 3x minus 28 is factorable into x plus 4 times x minus 7, which we knew ahead of time. So you can see then that synthetic division will work to factor a polynomial for you. And if it's a plus 0 at the end, then you really did just get the factorization, and you've got it factored. If it's not a 0 at the end, then what you got is just kind of a bummer of an answer. It's not factored, you didn't find out the x-intercepts, you didn't get anything good. But provided there's a 0 at the end, you genuinely did just take a polynomial and factor it. And remember, that's our goal. Our goal is to take a polynomial written in long form and factor it into a bunch of factors because that gives you the x-intercepts. Okay, I think that leaves us in a good position so that everyone can take a 10-minute break, take a nap, let your brain marinate on all this information. And when we come back, we'll try something new. The time is 9:05. Everyone be back at 9:15. And let's see here. Kevin Palacios, are you here? So Corey, did you go to discount time? Oh, it's 24 hours? Yeah, I had no idea there were 24-hour fire stations. So they were able to fix it for them. What's fine? So you just work on the pops. Yeah, did they find something in it?
It was literally like off. Like I don't know how many. Well, kind of off like
It was that flat.
that right here.
Yeah.
I mean,
Oh, crazy. Oh, so you drove on a flat tire?
it wasn't like where it was like ripped.
Oh,
It
geez.
wasn't- So like
Yeah.
this was ripped, but like it's not.
And then when you got there, they just put on a new tire for you? Oh, that was good. Gosh. You know, I always try to get to places first thing in the morning because I think, oh, I'm good.
Yeah.
But then let's say it opens at 7. I get there at 7:01. There's no five people on.
Yeah. Seems like.
And it's 24 hours. That's amazing. Gotcha. I'm glad you guys are taking it. Yes. No, I think this is the first time I'm signing something for you, right? Just so you know, my signatures go for $5 each. So you can pay me later, PayPal, anything like that. Yeah, electronic transfer to just. Do you know what you happen to have? Okay. Okay, you already filled those out. What's that say? No, it's oh, make. What does it even say? It's Dr. Lover. Yeah, but it says make. Sorry. Do you know what words these are? Well, is he going to see this again?
I don't think so.
Okay. Oh, because here it is. Oh, because he signed somewhere else. I got you. Okay.
Thank you.
You're welcome. Come back, folks. All right, folks, moving on. Let's turn to the page that starts off with the remainder theorem and the factor theorem. Some of what we're going to see now is going to be simple review of what we've already talked about. We've already covered a lot of ground, discussed a lot of theory, and the principles behind what we're doing. So, for instance, I'll just read these two with you. The remainder theorem. They're saying suppose P is a polynomial of a degree at least 1 and C is a real number, then when P of X is divided by X minus C, the remainder is P of C. Well, my goodness. That's a lot of really formal talk. What they really mean is the remainder theorem states that synthetic, the output of synthetic division is, let's say, well, geez, if you were to do plug in a number C into synthetic division, then the output is P of C. They're basically saying that you're getting the output. So the output of synthetic division given input C is output P of C. So it's what we've already been talking about. It's just saying that if you do synthetic division, whatever number you plug in at the beginning, the answer that you're getting is the same as if you plug that number into the function. And then with the factor theorem, they're saying suppose P is a non-zero polynomial, the real number C is a 0, if and only if X minus C is a factor of P of X. And that's also what we've been talking about. And if you have a polynomial, which is something like x to the 4th plus dot, 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 and you're able to factor it into something like this, then you know that that is an x-intercept, which is kind of the big general idea. Remember, our goal is to take any polynomial and factor it, and provided you actually do factor it into a bunch of factors, then they're all x-intercepts. And that's what the factor theorem is telling you, that if you're able to factor a polynomial, each factor is the x-intercept. So let's just try it. It says here, just a couple of examples. Determine P of C using the remainder theorem for the given polynomial. If P of C is actually equal to 0, then factor it. You'll see that this is quite simple from what we already know how to do. So here's our polynomial, 2x squared minus x plus 1, and they're asking us to plug in the number 4. Now notice, we're actually plugging in the number 4. We're not changing the sign this time. They're actually saying to plug 4 into synthetic division. So we have 2, negative 1, 1, and we're actually plugging in 4. So let's just see what it tells us. If I drop the 2, then multiply, add, multiply, add. Is that an x-intercept? Only if it ends in 0. Remember, what we just found out is the coordinate 429 is on the graph. That's what we just found out. We plugged in 4, we got 29. So therefore, no, that's not an x-intercept. The question was, determine P of C using the remainder theorem. We now know that P of 4 equals 29. That's the first thing they asked us to find out. They said determine P of C, C was 4, therefore, this is the first thing we know. P of 4 is 29, which therefore also means the coordinate 429 is on the graph, which is not an x-intercept. Then they say, if P of C is equal to 0, factor it. But it wasn't. P of C was not equal to 0, it's equal to 29. So we can't actually factor this polynomial. If we really wanted to, we could rewrite it the way we have been doing it. We could say 2x squared minus x plus 1 is actually equal to, now, the divisor in this case is x minus 4, and then this part right here, 2x plus 7, and then the remainder, 29. So that's the best that we could do. Again, using that process we just did. Remember these 3 parts. This part, you change the sign to put it into the binomial. Since we plugged in 4, the factor would be x minus 4. And then the 2x plus 7 is the quotient, and then the remainder is 29. So that's all we came up with. In that particular problem, all we know is that 2x squared minus x plus 1 can be factored into this because of a remainder. So these aren't x-intercepts at all. Let's try the next one. This is tricky. We've never plugged in a fraction before. That might feel a little unnerving to plug in a fraction. Let's just see how it goes. 8, 12, 6, and 1. And we're going to plug in negative a half. Enough to strike terror into the heart of a small child. Negative 1/2. It won't be that bad. These are all even numbers. So drop the 8. 8 times negative a half would be negative 4, right? Half of 8 is 4, and it's negative. And then add, so that's 8 again. 8 times negative a half is still negative 4. And then add, 6 minus 4 is 2. Half of 2 is 1, make it negative. Add, and that's 0. Hey, now this is exciting. This is a very exciting situation. We now know, input, output, that on my graph, I have the coordinate negative a half to 0, which is an x-intercept, right? Input, output, that's coordinate negative a half, 0. We have found a genuine x-intercept. That's exciting. We can write it down in a couple different ways. We could say P of negative 1/2 is equal to 0. We could also just say the coordinate negative 1/2, 0 is on the graph. Those are 2 ways of writing the same thing. That's just information that we get out of that process. But now, more importantly, we can rewrite this polynomial, 8x cubed plus 12x squared plus 6x plus 1. This is really exciting. This is our first example of a really nicely factored polynomial. Now we know that 8x cubed plus 12x squared plus 6x plus 1 is equal to, and remember our general formula, it's these 3 pieces of information. So first, that's negative a half, so we write down x plus a half. And then since our original polynomial was x cubed, we go down 1 degree and make this x squared x no x. That's worth watching very carefully, folks. Our original polynomial was x cubed, so now this part, this reduced polynomial starts at x squared. You go down from 3 to 2. Now that's the next part, 8x squared plus 8x plus 2. And the remainder is 0. That's really, really exciting. You know, in math excitement. Because we just took this cubic polynomial, which is not factored at all, and now it is factored a little bit, x plus a half, and then the factor 8x squared plus 8x plus 2. And the 0 at the end just goes away. So we have successfully pulled out one factor. You know, our ultimate goal is to make it look all the way like this. That's the ultimate goal, is to have just a bunch of factors. And we're not there yet, right? So theoretically, x squared is going to factor into 2 more factors. We're just not there yet. We would now have to proceed to factor 1 more time. I suppose we could ask, does 8x squared plus 8x plus 2 factor? We don't have to go that far. The point is just to show that synthetic division successfully allowed us to get 1 factor from this original cubic. And from there, we would just keep going. We would do the process over and over and over again until you finally have it chunked all the way down into those pieces. Now, I guess I am a little curious if that does factor, because if it did, that'd be kind of nice. That'd be 4x squared plus 4x plus 1, which is 2x plus 1. Is it really? Oh my gosh, it is. It does factor, folks. So just for the sake of showing it to you, this does factor the 8x squared plus 8x plus 2. It does factor into, if you pull out a 2 first, that's 4x squared plus 4x plus 1. And then that factors into 2x plus 1 times 2x plus 1. And just for the sake of you seeing it, that now gives us this, which is fully factored. The final answer would have been 2 times x plus a half times 2x plus 1 times 2x plus 1. And then you would say you achieved your goal. We achieved our goal because we want to take a general polynomial and chunk it down into nothing but binomial factors. And starting with this cubic, we did synthetic division once to get x plus a half. From here, I just factored out a 2, which gave me something that was factorable, and then that's our final answer. So here we go. This is the first problem where we've successfully done the whole process, which is to take a polynomial and break it down into its individual x-intercepts. Now at this point you might say, so we just used synthetic division to find the x-intercepts of a polynomial, which we could have done by graphing it on Desmos. And I would say, yep. Yeah, we did what we could have done by just using Desmos. We did it without using a graphing calculator. Okay. Oh, let's keep going. Anyone have any thoughts or questions right now? What do we have now? It says you're given a polynomial and one of its zeros, find the rest. Okay, this is going to be really exciting. We're at the point now where we can do the whole process and see the whole process. Again, you don't have a lot of space right there on your paper. You might want to use a separate sheet of paper or not. Maybe you can fit it all in there. Either way, this is going to be very exciting. All right. It says you're given a polynomial and one of its zeros. Find the rest of the real zeros and factor the polynomial. So let's start by making a goal statement, folks. Here's our goal. We want to take x cubed minus 6x squared plus 11x minus 6. And I want to factor it into how many factors? 3, because it's x cubed. Now, they did just tell us you're given a polynomial and one of its zeros. Circle that word 0 again. What does it really mean? The x-intercept. Remember, they use the word 0 flexibly to mean x-intercept. So, what's one of our x-intercepts? 1. Actual 1. They're telling us that's the x-intercept, 1. So if I were to go on my graph, I have an x-intercept of 1. What does that mean one of my factors is? X minus 1. So I already know this much. In terms of our goal, that's how much I know so far. Is that I've got a cubic polynomial, I want to factor it down into 3 binomial factors. I know one of them is x minus 1 because they told me that this c equals 1 represents the actual x-intercept. Okay, so now we do synthetic division. They told us that 1 is one of the x-intercepts, which means a coordinate is 1, 0, which means if I plug in 1, I should get out 0. So let's do synthetic division. 1, negative 6, 11, negative 6. And we're going to plug in 1. What should I get out? If I plug in 1, I should get 0. So let's see. Drop the 1, multiply, add, multiply, add, multiply, add. Remember, anytime you get a 0, you have to make it a smiley face. Smiley face because it means something great just happened. It means now that we know that if you plug in 1, you get 0, which means the coordinate 1, 0 is on the graph, which means you found an x-intercept. So now watch what this means. It means that the original polynomial, and you can write this all out again if you like, or you can just write the second part. The original polynomial, x cubed minus 6x squared plus 11x minus 6, is equal to the divisor, which is really x minus 1, and the quotient, which is, since we started at x cubed, again, you drop down 1 power, so it's x squared, x, no x. Now we have x squared minus 5x plus 6. If you wanted to, you could write the remainder of 0, but should we really write the remainder of 0? No, it's just 0, it goes away. And besides, our goal is to factor it. So this is what we've done so far. But our goal is to finish having all factors. And now all of you can, in your head, factor x squared minus 5x plus 6. 1 multiplies to make 6, that adds to make negative 5. This is another one of the tricky ones. It's going to be 2 times 3, 2 times 3, negative 2 times negative 3. Because negative 2 times negative 3 is positive 6, and negative 2 plus negative 3 is negative 5. So now we have that. And so we have figured out that x cubed minus 6x squared plus 11x minus 6 is actually equal to x minus 1, x minus 2 times x minus 3. That's a big deal. That's the core skill of this chapter. It's to take a polynomial and then turn it into nothing but factors. Because now I know where all the x-intercepts are. I have an x-intercept at 1, at 2, and at 3. My graph is a cubic, so I know that my end behavior is going up and then down. I also know my y-intercept is negative 6, so I can come on down here to negative 6, put my y-intercept. There's my end behavior. Each factor has a power of 1, so they all slice. And here's a picture of my graph. Again, I just want to say that if you were living in the 1600s and you were able to look at that and then make a graph, they would think you had godlike powers. They're like, oh my gosh, how did you do that? You must be some sort of genius. We don't even have calculators yet. I don't even know what electricity is. Right? In the 1600s, this would be a really big deal. Okay, let's try it again. And again, I want us to take us through the whole thought process. We have a polynomial. Our goal is to take that x cubed plus 2x squared minus 3x minus 6 and to rewrite it as something times something times something. And they're already telling us one of the x-intercepts. They're telling us that negative 2 is an x-intercept. And if negative 2 is an x-intercept, what's the binomial? X plus 2. Okay, so now we just need to find the other 2. In order to do that, we do synthetic division. We're going to plug negative 2 into our synthetic division. 1, 2, negative 3, negative 6. Because remember, if they're saying negative 2 is an x-intercept, then you're looking on a graph and you're seeing negative 2 is an x-intercept, that means the coordinate negative 2, 0 is on the graph, which means if you plug in negative 2, you should get out 0. So let's find out if we get 0. I drop the 1, multiply, add, multiply, add, multiply, add. Yep, it did give us a 0, which is what we expected. Now we know for sure the coordinate negative 2, 0 is on the graph, which means that is an x-intercept, just like they told us it was. And now, since we were starting as a cubic, my reduced polynomial starts at x squared, x, no x. And that means I can now go ahead and factor, right? Because the remainder of 0, we're just looking at these two terms. The negative 2 becomes x plus 2, the factor. And then this is the rest of the polynomial, x squared minus 3. So far we've factored it that far. How do we factor x squared minus 3? Or perhaps you still want to have it written down as x squared plus 0x minus 3. But I think it'll be easier if you just have x squared minus 3. That's a trickier one. I need to remind you a little bit about factoring. Who remembers how to factor x squared minus 25? This is called a perfect square binomial, or better yet, no, I'm sorry, it's called the difference of squares. You've got x squared, you've got 25, which is really 5 squared. How do you factor it? X plus 5, x minus 5? Does that look familiar, folks? One more example, x squared minus 9. That would be x plus 3, x minus 3. So what I'd like you to notice, though, is that you and I know how to do the square root of 25 and 9 in our head, right? What if you didn't know the square root? You would just say x squared minus 25 is x plus root 25, x minus root 25. That would be a formula that would be very simple to follow. And now, of course, you know the square root of 25 is 5. So if I gave you x squared minus 3, which is the problem in front of us, the actual formula is x plus root 3, x minus root 3. And that's how you do a difference of squares when that number is not a square. This is just a special trick. Maybe you've seen it before, maybe you haven't. But when you're doing a difference of squares, you're really just doing the square root of that number to be the numbers you put into the binomials. And in this case, you can't square root 3 in your head, so you just leave it as root 3. So, x plus root 3, x minus root 3. And we're done. We've achieved our goal. We were given a polynomial, and it's now broken down into 3 binomial factors. By the way, what are those x-intercepts? If you were to make a little graph, one x-intercept is at -2. Where's root 3 on the number line? You might have to do it in a calculator. What's the square root of 3? It's 1.7-ish. So really, we're going to have a 1.7-ish over here and a 1.7-ish over here. So those are our 3 x-intercepts, -2, -root 3, and root 3. And again, this is a cubic, so the end behavior goes this way and this way. We know the y-intercept is -6. And so our graph would go bloop, bloop, bloop. And that would be our graph. There's a lot of complexity here, folks. There's a lot of complexity. Like, for instance, keeping in mind that the number that you're plugging into synthetic division, you have to change the sign of that number when you're writing down the actual binomial. And that the bottom row of coefficients, you have to reduce the power of x by 1, so x cubed becomes x squared. And that in order to be even able to factor, you have to find the right number to plug in that it gives you 0 at the end. Right? So there's a lot of things that have to go right. These 2 problems are convenient because they told us the number to use. You'll notice they said, you're given a polynomial and one of its zeros. What if somebody had not come up to us and told us one of the x-intercepts? What number would we have plugged in? I mean, maybe 1, 1's easy. I mean, who knows? You know, how do we know what number to plug in to make it equal 0? That's a very non-trivial question. If I had not told you to plug in -2, how would you know what number to plug in to make it equal 0? Because only by finding a number that you can plug in and making it equal to 0 are you able to then factor it. So that's going to be the next question. How do you find what number to plug in? And I think, well, we're not there yet. They're still telling us the zeros. So let's practice a couple more times. These polynomials are getting a little longer. So I do want to keep doing them with you. Let's see, that's an x to the 4th, and this is an x to the 5th. How about I'll do the x to the 4th with you, and then you'll do the x to the 5th. And then we'll compare answers. So here we go. Number 5. Remember your goal. Here's a polynomial. I want to factor it into what? How many factors? 4. It's nice to write down a goal statement because you already feel like you know what you're doing. I want to take that polynomial and rewrite it as this. Now, what did they just tell us? Apparently, 1/2 is an x-intercept, and it has a multiplicity of 2. So if 1/2 is the x-intercept, what do I write down? X minus 1/2. And they're saying it has a multiplicity of 2. That means that in the polynomial, x minus 1/2 is being raised to the power of 2, which really means I also know this. I know that so far, because 1/2 is an x-intercept with a multiplicity of 2. Remember, multiplicity of 2 means the power on that particular x-intercept. So really, how close are we to our goal? We're already pretty close. We've already gotten 2 of those factors, and we just need to find the other 2. Questions about just that? Knowing what they just told us? They just told us that we have an x-intercept at 1/2. And since it's a power of 2, it bounces. And since it's an even, we know that our end behavior looks like a parabola. And we know that this one bounces. I just want you all to appreciate how much information we already have, and we haven't even done anything yet. All right, so we know we want to break it down into 4 factors. 1/2 is one of the x-intercepts with a multiplicity of 2, which means it's listed twice. And we know that our graph is going to end up looking something like this. Okay, so now what do? Now we do the actual synthetic division. So our coefficients are 4, -28, 61, -42, and 9. And we're going to use the number 1/2. Do I use the number 1/2 or do I use the number -1/2? We use the actual number 1/2 because where's the x-intercept? At 1/2, which means we have the coordinate 1/2, comma 0, which means if you plug in 1/2, you should get 0. So I'm plugging in 1/2, I should get 0. So let's try it. Drop 4, multiply, add. Multiply, add. What's 61 minus 13? Is it 48? Wait, is it really? 48? Yes, 48. Okay, multiply. Whoa, did I just do all that right? Multiply. And then add. What's that going to be? 16? No. 18. And then multiply. Add. Hey, that didn't work. What did I do wrong? Oh, that's a -18. So that's a -9, so that's a 0. Okay, so it did end up equaling 0, which it should, because they told us that it would. It's just synthetic division, but you might want to use a calculator. I just made a couple mistakes right there in my head. The calculator will help to make sure you're doing all that correctly. Okay, so what does that give us now? This is our reduced polynomial. We started with x to the 4th, so now it's x cubed, x squared, x, no x. So now what we know is that we have x minus 1/2 times 4x cubed minus 26x squared plus 48x minus 18. That's what one round of synthetic division gives us. We were able to chunk off one factor of x minus 1/2. So we call this part done, right? X minus 1/2, that part's done. That now tells us one of our x-intercepts is 1/2. This part we still need to keep factoring. So what do? We do synthetic division again. So I'm going to drop down those coefficients, 4, -26, 48, -18. And what number do we plug in? We plug in 1/2 again. We plug in the 1/2 again because they told us that 1/2 is a 0 with multiplicity 2. What that means is the 1/2 will work twice. You might want to say that. This number will work twice. It means that you can plug 1/2 into the synthetic division process twice, and it's going to give you a 0 both times. So let's confirm that. If I plug in 1/2, I should still get 0. So drop the 4, multiply, add. multiply, add, multiply, add. Great, it really did work. So that's what that means, that C equals 1/2 is a 0 with multiplicity 2. Means you're able to plug 1/2 into the synthetic division process twice, and it will still give you a 0 twice. So now where are we at? We had the x minus 1/2. That part was done. We now have another x minus 1/2. And we have this, which, since we were at a cubic, now we're at x squared x no x. And now we're at 4x squared minus 24x plus 36. That's where we are so far. Do you think that's why historically we refer to this as long division? Because it takes so long. I'm guessing that's why it said that. I wonder why they didn't call it tedious division. Am I right? Am I right? No? I don't? Okay. What can we do next? All we have left is just to factor this. What should we do to factor this? We cannot say what multiplies to make 36 that adds to make 24 because we have this coefficient of a 4. Can we factor the 4 out? Yeah. So let's take the 4 out all the way out front. So 4, x minus 1/2, x minus 1/2. Leaving behind with x squared minus 6, x plus 9. Now, can we factor that? What multiplies to make 9 that adds to make 6? It's just 3 and 3. So that gives us x minus 3, x minus 3. That was quite the process. But the really cool thing here is that it worked. So we achieved our goal. We took a polynomial and we factored it all the way down into a bunch of factors. And now let's interpret that. What's our final answer? If you were to write down the final answer, it would actually be 4 times x minus 1/2 squared times x minus 3 squared. And now how do we graph that? Oh, I can't move that up. How do we graph that? Where's one of my x-intercepts? At 1/2. And my other x-intercept? Is it 3? So let's plot that in, 1/2 and 3. And look at the multiplicities. An even multiplicity means the graph bounces. This even multiplicity means the graph bounces. So I've got 2 bounces going on there. The original was x to the 4th, so I know my end behavior looks like this. And now look how fun this is. The graph is going to bounce off of both of those x-intercepts. And you end up with boing, boing. And that's what the graph would look like. Then you might say, Mr. G, boing you. What do you mean, boing? Boing? Like, is this really how we talk about mathematics? You draw a line towards the next axis and you say, boing, boing? Like, is that really what we're doing here? Well, I mean, all I can really say is let's look at what the graph looks like. Here's the actual graph. So 4x to the 4th, 4x to the 4th, minus 28x cubed, plus 61x squared, minus 42x, plus 9. And what does the graph do? It boings. Right? It bounces right off the x-axis. It's exactly what we thought would happen. There's an x-intercept at 1/2. There's an x-intercept at 3. The overall end behavior is a parabola, and the x-intercepts are at 1/2 and at 3. So all the work that we did in fact successfully lead us to what the graph really does look like if you use Desmos to graph it. So, you know, I guess I'm pseudo-apologizing for my use of language when I say things like bounce and boing, because, well, yeah, that's what I see. That's what I see on the graph as you draw it. Okay, so we're done with that problem. Yep. That's what chapter 3 is about, folks. What we just did is what chapter 3 is about. So let's go ahead and do number 6. And then I think we'll say we call it done on this particular skill. I'd like you all to go ahead and try 6. And by that, I mean, go ahead and do synthetic division. And what number are you going to plug in? 1. How many times can you do it? 3 times. So you're going to do synthetic division 3 times using this process. So first of all, just everybody go ahead and do that. Do synthetic division 3 times. So you would have 1, 2, 3, 12, 38, 37, 12. And you're plugging in -1. And you're all about to do that process 3 times in a row. And of course, if you're doing it right, what number should you end up with? 0 every time. So go ahead and do it 3 times. Oh, sorry, thank you. Yeah, boy. Make sure you write down the coefficients correctly. 1, 2, -12, -38, -37, -12. Well, your work looks really good. Your notes look fantastic. Folks, did the first one work? It did? Gosh, I must have really made a mistake. -1. Oh, that's it. There we go. Aha. Aha. Okay. All right, folks. Should we compare work? And what information we got out of this process by doing synthetic division 3 times in a row using -1. So the first time you did it, you used the coefficients from the original problem. And did you end up with the coefficients 1, 1, -13, -25, and -12? So that first thing that you just did, step 1, told us that one of the factors is x plus 1. Because remember, you changed the sign. -1 is the x-intercept, so the factor is x plus 1. And then you use that reduced row of coefficients because you started as x to the 5th. Now you're x to the 4th, x cubed, x squared, x, no x. And so now we know this. It's just our first step. Using synthetic division once, you get one factor, and you're still left with a really long polynomial. So then what do? You take the coefficients from that polynomial and use those coefficients to do synthetic division again. So again, we're plugging in -1. You do synthetic division. Did you end up with 1, 0, -13, -12? And then that itself is a reduced polynomial. So since that polynomial was x to the 4th, you reduce it now to x cubed, and now you have this information. You have 2x plus 1s now, because we've done it twice, and the resulting polynomial was x cubed plus 0x squared minus 13x minus 12. Now they told us that -1 was an x-intercept with multiplicity 3, so now I can do synthetic division yet again using those coefficients from that reduced polynomial. So now we have 1, 0, -13, -12. We're going to do -1 again. And that reduces us all the way down to 1, -1, -12. Notice all of these end in 0. And that's where we end, is that we've successfully done synthetic division 3 times using -1. And the last polynomial that we have is x squared minus 1x minus 12. This is the way of things with synthetic division, is that you keep doing synthetic division until you finally get down to a quadratic, which you know how to factor off the top of your head. So how do you factor this off the top of your head? What multiplies to make -12 that adds to make -1? Is it -4 and +3? So that's the end of the problem. We have completely factored our original x to the 5th, which is a quintic polynomial. We took our quintic x to the 5th polynomial, broke it down into 5 factors. And I'd just like to point out, to finish the problem, you graph it. Because remember, that's the whole point. Our goal is to take the behavior on the y-intercept, factor it so that now you have the x-intercepts, and now you can make a really good graph. So let's make that really good graph. A really good graph has the y-intercept, the end behavior, and the x-intercept. So first I'm going to rewrite this with the multiplicity. So that's x plus 1 cubed times x minus 4 times x plus 3. And so my x-intercepts are at, our x-intercepts are at -1, and at 4, and at -3. Right? So far that's what we know. We've got x-intercepts and -3, -1, and 4. If you look at the multiplicity, all of our multiplicities are what types of numbers? They're all odd. 3 is odd, 1 is odd. So each of those x-intercepts is going to be a slice. So each of those is going to be a slice. All are slices. Okay, what else do we know? This was a quintic, x to the 5th. What's the end behavior? The end behavior is up to the right, down to the left. And finally, we should put in the y-intercept. What was our original y-intercept? -12. So we can put that on our graph as well. I'm just going to put a dot down here towards the bottom. There's -12. And now we are completely ready to connect the dots, la, la, la. So I'm going to go slice, slice through the -12, slice, and up to infinity. And there's a really good graph. This is the point at which you would say, you're done. That's the point of everything that we've done in chapter 3 so far, is to take a polynomial, x to the 5th plus 2x to the 4th, etc., and then to break it down as a graph. Which, of course, you did using that one. But this way you're doing it with all of the skills that we've learned. Questions about this process? It's a rather lengthy process, isn't it? I mean, really any one problem would take up about a page, maybe, about a page of line paper to do all the synthetic division, rewrite it all, draw a graph. Yeah, it really would. Now, again, at this point, they have been telling us an x-intercept. Isn't that nice of them? They just came up and told us that -1 was an x-intercept. So what if they don't tell us what the x-intercept is? That's what we're leading up to. All right. These are a different type of problem. I don't think we need to do too much synthetic division right now. They're just asking us to create a polynomial. These kind of look like word problems, don't they? Yeah, they're not word problems, and they're actually pretty straightforward. Let's look at that first one. It says, let a polynomial p of x which has the desired characteristics. So I want a polynomial whose zeros, which you all know means x-intercepts, are plus or minus 2, plus or minus 1, and the leading term is 117x. So first of all, we know that we have the x-intercepts -2, +2, -1, +1. So let's write that down. You know you have an x-intercept there. Does everybody agree with that so far? Those are our x-intercepts. If I were to multiply all that out, it would start with x to the 4th, and it would end with 4. Does everyone agree with that? If you did take the time to multiply it out. We don't have to, just if we did. Okay, well that's what the polynomial would be, but they're saying that I want a polynomial whose first term is actually 117x to the 4th, which means I only have to do one more thing, which is to write 117 in front of it. Because that way, when I do multiply the whole thing out, I would get 117x to the 4th plus 468 at the end. Because 117 times 4 is 468, right? That's it. All we know now for sure is that this is a polynomial that has the x-intercepts of plus or minus 2, plus or minus 1. The leading term is 117x to the 4th, and it has a y-intercept of 468. So actually we know a lot. Let's try another one. The next one, the zeros are 1, 3, and 3. So that 3 is listed twice. And the leading coefficient is -5. So let's write down what we do know first. The zeros are x minus 1, x minus 3 squared. Right, because the x-intercept of 3 had a multiplicity of 2, so we just put that one in with an exponent of 2. And finally, they're saying the leading coefficient is -5. So if I were to multiply that whole thing out, I would get x cubed plus something, something, something minus 9. I don't agree with that. Because imagine if you had x minus 1 times x minus 3 times x minus 3. Remember, you get the y-intercept by multiplying all 3 numbers. So a negative times a negative is positive, times another negative is negative. So that's what we would have. But they want us to have a leading coefficient of -5. So that means we'd have to put a -5 in front of that, which would change these two coefficients to what? -5x cubed plus something, 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 plus 45. So that's what we know. This is what our factored polynomial looks like. That tells us the x-intercepts. The leading coefficient tells us the end behavior. It's an upside down one. And if we were to multiply it all together, we'd have -5x cubed plus something, something, something plus 45. Okay. So we call that building a function with the desired characteristics. You notice that's what they said. Write a polynomial with the desired characteristics. I'll tell you desired characteristics. Okay. So let's try number 9. It says the polynomial of degree 4. So what does that tell us? We want we want a polynomial of degree 4, so I know that I have p of x equals with 4x intercepts, and or my p of x is going to be x to the 4th. I just write this down so that you all kind of see an end game. Right? As soon as they say it's a polynomial of degree 4, you can go ahead and imagine that it's either going to be factored with 4 factors, or it's going to start with an x to the 4th. Right? And these are the things that I hope come to mind for you. And when you read the polynomial of degree 4, your mind is not just blank with the sound of wind. Right? Go ahead and imagine, what does that mean? A polynomial of degree 4, it either means it's factored with 4 factors or it starts with x to the 4th. It's helpful to write these things down to give you more of an idea of where to go. Okay, so now what? It has a root. What does the word root mean? Yeah, 0 or x-intercept. So it has a root of multiplicity of 2 at 4. So now I know this is x minus 4 twice, right? Which really means when I finish writing it, it's going to be x minus 4 squared. So it has a root of multiplicity of 2 at x equals 4, and the root of multiplicity of 1 at 0 and negative 2. So that means my other x-intercepts are x minus 0 and x plus 2, which x minus 0 is really just x and x plus 2. So far, that's what I know. Could we go ahead and say what the y-intercept is going to be? In your head, real fast. 4 times 4 times 0 times 2. 0. So we know that that's what our polynomial is going to look like. The one thing they haven't told us yet is there a leading coefficient? Remember in the first problem, the leading coefficient was 117, and in the second problem, the leading coefficient was negative 5. Did they tell us what the leading coefficient was yet? They did not. So we're going to introduce the leading coefficient variable, which is C. C stands for a leading coefficient if there is one. Right? If there were a leading coefficient, it would just be some number sitting in front of the polynomial. We don't know what it is. It could be as easy as 1. It could be that the leading coefficient is just 1. But it could be that the leading coefficient is 117 or negative 5. We don't know. We introduce the letter C just to say, hey, there could be. Right? Hey, there could be a leading coefficient. They didn't tell us yet, but there could be. Okay, well, there's one last thing that they're telling us, and that's that the whole graph goes through the point 5, 7. So now what is that? The whole graph goes through the point 5, 7. 5 is your x, or your input, and 7 is your output. So let's just take a look here, folks. I would take this one now, and let's rewrite it again. P of x is equal to something times x minus 4 squared times x plus 2. Now write this down with me very carefully, because I want you to see how this process works. If I plug in 5, it should equal 7. So watch. If I plug in 5, it should equal 7. And I should have done that in blue. So we'll go into it. Plug in 5, it should equal 7. What we're about to do right now is figure out what that C value is equal to. Is there a leading coefficient? So let's just look at this part right here. Let's focus our attention in on the function equaling 7. I want that thing to equal 7. So there could be a C value, I just don't know what it is yet. So first of all, 5 minus 4 is 1, 1 squared is 1, and that's just 5. Then 5 plus 2 is 7. So far I have this, that C times 1 times 5 times 7 is equal to 7. Now I can multiply all that, and so far I have 35C is equal to 7. I just multiplied all those terms on the left. And if I solve for C, that tells me that C is equal to 7/35 is 1/5, or 0.2. that whole procedure that we just did there, them telling us that it goes to 0.57, was in order to solve for C, to find out if there was a leading coefficient or not. Was the leading coefficient just 1? Was it 117? Was it -5? Actually, it's 1/5. So now we can go back and say that our final answer is 1/5 x minus 4 squared times x plus 2. And that is our final answer. I'd like us all to appreciate what we just did. All these examples say to write a polynomial which has the desired characteristics. So let's just look. I'm going to go ahead and graph the polynomial we just came up with. It's 1/5 what was it? X minus 4 squared times x plus 2. Plus 2? Yeah, plus 2. Okay, well, let's take a look at our polynomial. Does it have the desired characteristics? First of all, does it have an x-intercept at -2? Yes. Does it have an x-intercept at 0? Yes. Does it have an x-intercept at 4 that bounces? Yes. And then the bigger question, does it go through the coordinate 5, 7? Well, let's find out. If I can get my cursor to go. Oh, there it is. Does our graph go through the coordinate 5, 7? Yeah. So there we go. We just pieced together a function that has all the characteristics that we wanted it to have. And you might say, that's boring. I know none of you would say that. But what it really is powerful. That's very powerful that you're able to create a function that has all the characteristics you want. Because then you could use that function to, say, model supply and demand in an economy and know what happens if you change the price of your product by increasing it by $100 and what that's going to do to your demand and how many people are going to buy it. So that's just an example of why you'd want to be able to build such a thing. Okay. I'm going to set number 10 up with you. Let's set up number 10. And then we'll move on. We've got a polynomial of degree 3. So what do we know so far? We've got 3 factors and a leading coefficient of C, though we know not what it is. That would be just taking the information, polynomial of degree 3, demo. You'd write down that. That's what that means. We have a polynomial of degree 3. You have 3 factors with a C up front. That's your leading coefficient. It has a root of multiplicity 2 at x equals 4. So if you were to think about a graph, that's the x-intercept 4. So therefore, and it has a multiplicity of 2, so it bounces. Then we have x minus 4 twice. Right? Since the x-intercept is a positive 4, the factor is a negative 4. And finally, it has a root of multiplicity 1 at x equals -1. Since the x-intercept is at -1, that means we're actually putting x plus 1. It is a cubic, you'll notice. And so far, this is what our graph looks like. Is that a reasonable interpretation of everything that it's done so far? It's a cubic. It goes through 1 was a slice, -1 was a slice, 4 was a bounce. Okay, and finally, they're telling us that the y-intercept is -8. What is a y-intercept? Well, shoot, I have this graph drawn badly. Oh, because the leading coefficient could flip all of this. And so the actual graph probably looks like this. Because that way we'd have a y-intercept of -8. So already we can kind of tell that we should have a leading coefficient that's negative. Well, let's just see how it works out. If the y-intercept is -8, that means the coordinate is 0, -8. Which means what? If I plug in 0, I should get -8. So let's do it. If I take my polynomial and write it empty, and I plug in 0, what should it equal? -8. So once again, this problem is all about solving for C, the coefficient out front. What is the leading coefficient? So what does that leave us with? We have C times -4 times -4 times 1. All that should equal -8. if you want to make a note to yourself, this whole problem is about solving for the leading coefficient, C. Now, honestly, once you get it all set up, I mean, this is just basic algebra, right? You multiply all that together, and what do we get? 16C equals -8. And so C is being multiplied by 16, you divide by 16, and we get C equals -1/2. And that's it. Now we can write down our final polynomial. Our polynomial is p of x equals -1/2 times x minus 4 squared times x plus 1. That is a polynomial that has the desired characteristics that we wish. So I just want to confirm that for you. I'm sure that you're all on the edge of your seat. Graph it, Mr. G, graph it. Let's see, does it really work? I'm sure that's what everyone's thinking. X minus 4 squared, x plus 1. We're all on the edge of our seat. Here we are. There's an x-intercept at 4, which has a bounce. There's an x-intercept at -1, and there's a y-intercept at -8. So our polynomial really did have all the characteristics that we wished. And that's the whole purpose of this exercise, is to build a polynomial that has certain characteristics. Okay, I have 5 minutes. That gives us just enough time to finish 3-2. And then when we come back next time, we'll do 3-4. Yeah. Okay, we're doing great. The timing that I predicted is a little off. I mean, what I put into our calendar is really just a prediction. Hold on, let me go back up here. When we started all this, hold on, I predicted, there we go. I predicted that we'd be on 3-3 today, but really we were on 3-2 today. No big deal, we'll catch up. So let's finish these last 2 problems. Where are we? Yeah, these little graphs. Let's look at these little graphs. We've got 5 minutes, we can do both of these. And folks, I really want to impress upon you that this is impressive. I realize me saying that might not impress you. Like, guys, this is impressive. Maybe you're like, no, I don't think it's impressive. But it really is. That what we have in front of us here are 2 graphs of wiggly lines, right? Here you go, Merry Christmas. Here's 2 graphs of wiggly lines. And I'm telling you, I want you to write down a function that looks like that. Okay, that's incredibly powerful and impressive. I'm just saying, there's a squiggly line, there's a squiggly line. Come up with a formula in terms of x that if you plug it into Desmos, it actually looks like that. That's really impressive. It really is. It's an extraordinary amount of mathematical power. Whether you believe me or not, it's really impressive. So let's look. What do we have here, folks? We have our x-intercepts. Are they slices or bounces? We've got 1 bounce. I would label all this, folks. And I've got a slice. And a slice. And furthermore, we also know a y-intercept, which is going to prove to be very helpful. And we know the whole thing appears to be an upside-down parabola. So let's write down what we can. f of x is equal to what? We've got an x-intercept at -2, so that's x plus 2. And it's a bounce, so I'm going to give it an even multiplicity. We also have an x-intercept at 2, which is x minus 2, and at 4, which is x minus 4. Those are slices, so I'll give it an exponent of 1, which we can really just ignore because it's just a 1. That's what we know so far. Furthermore, there is a leading coefficient. We just don't know what it is. It could be 1 for all we know. But we can't just assume it's 1. We have to say, okay, if there's a leading coefficient, call it C. Now we have to plug something in for x so that we can actually solve for C. And always the easiest thing to plug in for x is 0, which represents the y-intercept. Keep in mind the y-intercept is 0, -2. Which means if I take my function now and plug in and write it empty, f. You take your function and plug in 0, then what should it equal? -2. That's what the y-intercept tells us. If I plug 0 into that function, it better equal -2. And so this helps us solve the leading coefficient. So c times 2 squared is 4, times 0 minus 2 is -2, times 0 minus 4 is -4. So far we have that. Notice I just did 0 plus 2 is 2, 2 squared is 4. So now I multiply it all together. 4 times 2 is 8, 8 times 4 is 32. Negative times negative is positive, so now that's 32c equals -2. And dividing off of 32, we get c equals -116. So what does that tell us? Our final answer is that if I told you, here's a graph of a squiggly line, give me a function of x that actually looks like that if you graph it, it would be f of x equals -116 x plus 2 squared times x minus 2 times x minus 4. And that would actually look like the graph that we had in front of us. And again, that's enormously powerful, that's enormously sophisticated, that's pretty impressive. Be able to take a picture of a squiggle and write down a function that actually has all those key characteristics, namely the same x-intercepts, the same y-intercept, and the same end behavior. You notice the end behavior worked out, it's negative. It's a parabola facing down. So given time constraints, I'll just set this one up for you. I would go through, mark all of your x-intercepts, and say, this is a slice, this is a slice, this is a bounce, this is a slice. And therefore, so far, our function is the leading coefficient of x plus 3 to the first times x plus 2 to the first times x minus 1 squared because it bounces, and x minus 4 to the first because it's a slice. So there you go. That sets up your problem. And you have to look at your y-intercept, which is -1, so that really means if I plug in 0, I should get -1. So again, if I plug in 0, what's so great about plugging in 0? It's just all the numbers, right? If x is 0, it's really just 3 times 2 times etc. So that's 3 times 2, -1 squared is 1, 4, and all of that should equal -1. And that will allow you to solve for c. I know the class is over. We're so close to finishing this problem. I'm sure you all want to write down the end of the problem. So 4 times 2 is 8 times 3 is 24. So that's 24c equals -1. Oops, that was a -4. So therefore, that's a -24. And therefore, c is 124. Which tells us our final answer is f of x equals 1/24 x plus 3 times x plus 2 times x minus 1 squared times x minus 4. And that's your final. Okay, well, good gumdrops. I'm so glad we finished 3-2. Now I can say to you, your homework on 3-2 is due next Monday. When you come back to class on Wednesday, we'll do section 3-3 and 3-4. And I have papers to pass back to a few of you. Alexis and Kevin. No Kevin today. Jennifer, there you are. Zeri. Corey. Thank you, folks. I have office hours right now if you want to come up.
Right now. No.